Swayam Prabha. Digital India. Educated India.
In addition to the size requirement for the fillet welds, there are also some requirements for the length of the fillet weld as well as the groove welds. So first we will talk about the groove welds. So if we do a groove weld, the effective length should be at least 4 times the effective throat thickness of the groove weld, whether it is a full penetration, CJP, complete joint penetration, or a partial joint penetration type of a weld. The Indian code IS 800 prescribes that requirement in clause number 10.5.4.2. Also, this dimension should not be less than 40 millimeters. So at least 40 millimeter weld should be provided at a time. Any weld that is less than 40 millimeters is not qualified as a proper structural weld. It is only a tack weld. If it is a fillet weld, again a similar requirement is there. If in such a case, in a fillet weld, instead of using the throat thickness, which was actually the equivalent of throat thickness of the groove weld, the requirement is that the weld length should be at least 4 times the weld size. So weld size is A, which is this dimension, 4 times that, at least that should be the length of the fillet. In both these cases, however, there may be a situation where the weld of length less than 4 times the weld size is provided. If that is the case, for design calculations, we should consider that length as the effective length, whatever is provided, and reduce the size of the weld in such a way, for our design calculations, reduce the size in such a way, which is the size of the weld is 1/4 of the length of the weld. So for example, if we are providing an 8 millimeter weld, if we are providing an 8 millimeter weld, but the length of the weld we have provided is only, let's say, 24 millimeters. So this does not satisfy the requirement of length, effective length should be greater than 4 times the weld size. Then what do? We take this as the effective length, and then the A effective will be reduced to 24 divided by 4, which is 6 millimeters. So for our design calculations, we will not use the actual size of the weld, we will use only 6 millimeters. So we will reduce the weld size. Also, one must notice that whatever weld we provide as per the design and the drawings, the welder at the site will also add some length to that weld, and an additional at least 2 times the size of the weld is usually added to the fillet weld on each side. There are also some requirements about the placing of the welds in terms of how far apart the welds can be in the direction of the load, in the direction perpendicular to the load, and so on. So here is an example of 2 plates that are being fillet welded together through a lap joint. So this is a flat plate. It does not have any angle or anything, any protruding part outside. And if it is subjected to a tension force demand, there are a couple of requirements for it. One is that the length of the weld should be at least equal to the width of the plate. That is, width of the plate is actually governing the spacing of the 2 fillets which are resisting the load. This is basically required to reduce the stress concentration. If this weld is very small in comparison to the width, the edges of this weld will be under very high stress. Therefore, at least a certain length of the weld is provided so that those stress concentration at the edges can be minimized. In addition to that, the width of such a plate, which is being resisted through fillet welds only at the ends, the width of this plate should not be greater than 16 times the thickness of the plate. What happens if the plate is wider than the 16 times the thickness of the plate? In that case, when the load is being applied, there is a very significant shear lag effect. The load is acting everywhere. So it is away from the weld, it is uniformly distributed. But as we come closer to the welds, most of the force is getting transferred from the edges, because that's where the weld is. And there will be very large shear lag effect in a way that will reduce the strength of the bar too much, or the strength of the weld connection too much. So in order to minimize that shear lag effect, we should make sure that this width W is not more than 16 times the thickness of the plate, is less than 16 times the thickness of the plate. If, however, if this width is more than 16 times the thickness of the plate, we have to make sure that these plates are not only welded at the edges, but it is also welded at the end, or also we may use plug or slot welds along the length and width of the plate, and join the two plates together through those plugs. That will allow us to distribute the force more evenly between the plates through welds. If we are going to use intermittent welds, which are often required because the load requirement is sometimes very low and we don't have to cover the entire length of the weld using full size weld, continuous weld, so we may have to often go for intermittent welds. However, we should avoid those intermittent welds in case of dynamic loading conditions. Why? Because as we discussed, the edges of the ends of any stretch of a weld are the areas where high stress concentration takes place. So if we provide intermittent welds, that means we provide welds in smaller sections, several small welds, which will produce several areas of high stress concentration, and we should try to avoid it. So especially if the structure is subjected to dynamic type of loading conditions where there is a possibility of fatigue, we should avoid intermittent welds. Again, the individual welds should be of at least 4 times the weld size length, as we have discussed before for a regular weld. In addition to that, the clear spacing between two welds should be not more than 200 mm, or should not be more than 16 times the plate thickness or 12 times the plate thickness, depending on whether the welds are in tension or compression. So if the welds are in tension, that is, if the members are subjected to tension, they are being pulled apart. In this case, the S value should not be more than 16 times the plate thickness, this plate thickness, and should not be more than 200 mm. Both conditions have to be satisfied. If the weld is subjected to compression, then this S value cannot exceed 12 times the plate thickness or 200 mm, whichever is less. As a designer, we should be mindful of this fact that terminating a weld can be a critical factor in the overall performance of a structure. So generally, it is not preferable to terminate a weld, that is the end of a weld, being located at a position where there is already a perpendicular edge. So for example, between these two options, here you can see there is a horizontal plate in both cases, and there is a vertical plate which is being fillet welded with each other. Now, it is general understanding that the second option is a preferable one, even though the first one is also acceptable, but special care needs to be taken, and therefore it is not really preferred option. If one wants to continue the weld all the way to the edge, it is better to continue the weld all the way around, and that might be a better option. Why don't we continue the weld all the way to the edge and stop? Because then the quality of weld right at this location kind of becomes very difficult to assess, and there is a very high probability that the quality of weld would not be good. There will be some kind of an undercut. Some of this parent material would melt and leave a sharp corner there. So therefore, it is generally preferred that we stop the weld at least one weld size away from the edge, and that's how we should design the welds. So if we require the weld to be slightly shorter, that means we may have to increase the weld size to compensate for that reduction, but we should prefer not to come all the way to the edge and stop. If we have to come to the edge, it is much better to just continue all the way around. Similar example is shown here again. So this type of a situation, in fact, this is if one of the plate is extending beyond the other plate. In such a situation, it is not even acceptable to stop the weld at this edge. It is in fact mandatory to stop the weld slightly before that edge, because again at that edge there is a possibility that edge may melt away and will reduce the overall cross section, and also it can lead to unwanted sharp corners in that location. Similarly, like these, also there can be a possibility where we have to weld or provide fillet welds in the opposite faces of a common plane. So for example, here you may see these two welds are basically between this flange and this plate, under the plate, and this weld is again between this flange of the beam and this plate, but this is above the flange. So these two welds are on opposite sides of the plate, and in such a situation it is better to not make them continuous. It is better to terminate them separately. Again, the risk here is because of this sudden change in direction of the weld, where it has to turn in two planes simultaneously, there is a very high likelihood that a large portion of this plate will be melted away and we will be left with a weak cross section there. That's where the failure may begin. So mostly these requirements, termination of the weld, are governed by the workmanship related issues. There are, however, some situations where we may actually want to not terminate the weld right before the end, but continue the weld slightly farther and then terminate it. Such a situation is called an end return. An end return. This end return type of a weld is particularly useful in such scenarios. Here I am showing you through an example. Let's say the same weld in this connection you may see there is a beam which is connected to a girder, and this connection is through a cleat angle. So there is a single angle here. Maybe there can be double angle connection also. The two connections behave in a very similar fashion. So if let's say there are double angle connections, so there is a double cleat connection, so both angles are welded to the girder web and they are bolted to the beam web. The weld between the angle and the girder web are shown here as this fillet welds. This is this portion of the fillet weld that is shown as a triangle here, right? Now, generally such a connection is designed for a vertical load, right? That is a shear load primarily. And if shear load is the only load acting on this weld, even if it is not returned at the top and bottom, it would perform perfectly fine. There is no challenge, there is no issue. However, in such a scenario, you might realize that this connection behaves almost like a simple connection. And if it is a simple connection, this at this end, the beam is likely to rotate, because at simple connections, the beam ends can rotate. They cannot resist moment. And if it is going to rotate, this is going to lead into some kind of a pull force acting at the top edge of this angle, which is shown here. So if you look at the top edge of this angle from the top, looking from the top, this angle at the top will be bending or deforming like this. In such a scenario, this particular fillet, you might notice, has a moment acting in its longitudinal axis, which is basically causing it to pry open right at the root, which we have, as we have discussed before, is not a desirable way of loading of this connection. Now, this type of a loading that is happening in this one is not really the intended type of loading, because this weld is primarily designed to resist the vertical load only. However, there can sometimes be some unintended type of loading which can introduce these stresses, and these stresses could be very bad for the health of this connection. So in order to prevent this kind of a stress concentration, it is advisable to not terminate the weld before the edge or before the corner, but it is better to go around the corner slightly and go at least by a distance which is at least 2 times the weld size or less than 4 times the weld size. So there is such recommendation available in the international codes which recommend us to go at least this much of the depth inside, particularly on the side where there is a possibility of prying action. Therefore, often this type of a weld is provided only on the top and may not be provided at the bottom, because in a simply supported beam, we are likely to have tension at the end or a prying opening at the top, and that's where this has to be continued at the top. Okay. Why don't we weld the entire width of the angle at the top? Because also we want this connection to continue to behave like a simple connection. So if we weld the entire width of the angle, that will effectively restrain the movement completely and would again introduce areas of sharp stress concentration. Therefore, we weld only up to a certain width, which is considered as 4 times the weld size, and at that point we stop, so that the rest of the angle, so let's say the weld is this much of width of angle is already welded, the rest of the angle is still free to deform and as a result produce some level of flexibility in the connection. As we just discussed, the fillet welds behave somewhat similar fashion as the partial joint penetration welds. So fillet welds, since they provide a welding between two perpendicular surfaces, and there is always a portion of the combined surface which is not fused together, and in whether the welding is done on one side or whether it is done on the two sides, in both cases there will always be some portion of the surface which will not be fused together, and that's where the cracks can start. Okay, so we have to be mindful of the situations where the crack can begin here, and we have to make sure that such type of loading situations should not arise. So here, through an example, we can understand if we make a built-up section which looks like this, and if there is a possibility of a load acting like this on this flange, we might realize that this will again lead to a opening of the root in this weld, which is not a desirable outcome, right? Because that's where the crack can very easily start. However, this can be prevented easily by one of the two ways. Either we can provide stiffeners here. So if we provide stiffeners here, these stiffeners can carry the load directly and transfer it. If the stiffeners are welded to the flanges, these stiffeners can transfer the load to the bottom flange without having to rely on the or without having to transfer bending moment to this weld. Alternatively, we can provide double-sided welds. So double-sided welds do offer some level of rigidity. So if the moment is applied here, there is a decent amount of lever arm available now in this case in comparison to what was available here, and as a result the stress concentration at the root is minimized. So this recommendation is available in our Indian IS 800 code also, which specifically states that single fillet weld should not be subjected to movement about the longitudinal axis of the weld, and the same guideline is specified in the American design guide also, which specifies that rotation about the root of a single-sided fillet weld must be prevented. We will briefly discuss the issue of plug and slot welds. We had also described it in the beginning a little bit. So basically what happens is that plug and slot welds are not really very frequently used type of welded connections. They are actually a variation of fillet welds. So in a fillet weld, we typically provide a weld along an edge. In a plug or a slot weld, so what you see here is a picture of a plug weld where you have two plates. This could be the gusset plate and this is another bar which is to be welded to the gusset plate. We drill a hole in the bar only and then we place it, and then that hole is filled with the filler material, welding material, and as a result what you see here in orange color, this small line is basically the new root of this weld, and that's where the failure should be happening, and that will control the design strength of this weld. So such welds are not typically provided for resisting regular tension or bending moment situations. However, they are very useful in situations such as the one shown here. So for example, in shear zone, shear dominated zones, which is typically seen in a shear panel section of a column which is subjected to large bending moment demands under earthquake conditions, for example. In such a situation, this shear panel needs to be stiffened. One option to stiffen that shear panel is through providing a doubler plate. This doubler plate is expected to deform along with the web of this column. If we weld this doubler plate only on the outside 4 edges, there is a possibility that this plate will buckle independent of the web, and therefore the total overall stiffness of the panel will not increase sufficiently. One option to prevent that is actually to drill holes in this doubler plate at a few locations and then weld and provide this kind of a plug welds to combine the two plates together. So through these type of plug welds, we can make the two plates behave simultaneously, deform simultaneously. So in such a situation, shear dominated situations, they are more frequently used.